Good afternoon, everybody. Welcome to the free seminar, second one of this week. Going to be a great pleasure to introduce Bram Hoex today. Of course, we all know, but I'll just say a few things about him. So Bram, of course, has been with us now since 2015, back in the school. He did his undergraduate and master's degrees and PhD at the University of Eindhoven in 2005 and 2008, I think. Then he's actually here for a brief period during that time, approximately 6 months, I think. 3 months. 3 months. Okay. It was. It felt. You made a great contribution at that time. I'll put it that way. You did, in fact, actually. In particular, remember the ellipsometer that you engineered for us coming in, which was very useful. So he then went to Ceres and became the. Started off as the. You ended up as the research director at Ceres, the Solar Industrial Research Unit in Singapore, and where he did some amazing work. And much of the work that Bram is famous for is instituting the use of aluminium oxide as a passivation layer and serving many other purposes in TOPCon and PERC cells, and providing a huge increase in the performance of those devices. So this is a very important part of the work. He has, of course, contributed to much other work. Since coming here in 2015, he's done a large amount of work in those areas, and now is the deputy head of school for research. And very much looking forward to his talk about the field work on decoding degradation at the cell level. So, Bram, we're very much looking forward to your talk. Thank you.
Thanks, Kevin, for the very kind introduction. And it's very nice to give a seminar today about the work that we did in the last probably 3 years, all at UNSW with our industry partners on reliability. So why do we care about reliability? Because typically you don't get press releases with reliability. So typically you get press releases with the efficiencies, which are shown here. But then if you look at the LCOE, so the levelized cost of electricity, that also is dependent on how stable your technology is. And this is a publication from my former colleague, Marius Peters, showing where you have basically equal LCOE with a starting efficiency and a continuous degradation rate. And you see if your degradation rate goes up, you really have to start a lot higher to obtain the same LCOE, let alone about inverter and clipping and stuff like that. So that's something we don't even consider. So it really pays off to basically have a low degradation rate, because then even with a 20% silicon module, you could be basically cheaper than a silicon perovskite tandem that would be at 35% starting efficiency if it would decrease by 3%. It also means that it could pay to put money into reducing the degradation rate, although it's always hard to capture that from the market, because it's very hard to measure. How do you measure 25 years? And I will show a bit of that in the presentation. So if we then look at basically the dominating technologies now, so PERC had its time, so Martin, very good work. So it was basically still more than half of all the modules out there are PERC, but currently the market is dominated by passivated contact solar cells, so TOPCon and heterojunction. And this is work that we published only, I think 2023, where we looked at basically using cheaper encapsulant and a backsheet for heterojunction solar cells. And we saw only after 1,000 hours of damp heat testing, we saw a lot of failures popping up. And these failures are shown here in EL images. I assume all of you are familiar with electroluminescence. Bright is good, dark is bad, and dark could be series resistance or recombination losses. So clearly, these heterojunction modules are not happy after only 1,000 hours in the damp heat chamber. And also, the signature of this degradation is different than we saw with PERC. And that was a bit scary, because all the tests we had at the cell level were aimed at what we could see in PERC and aluminum back surface field. So this was a big spark for our research. So basically to see if we could understand those a bit better. Is TOPCon any better? Not probably if you've seen my recent news articles, etc., then it's not a surprise that TOPCon also has an issue. This is actually a glass module made by our partner JA Solar, published in 2023, so not that long ago, where they tried to go to EVA as the encapsulant. So typically TOPCon is sold with PUE, which has a lower water vapor transmission rate. If you then try to replace this with EVA, then you see that, again, this EL image, the module gets darker from the sides, and that's where the water comes in. If you have glass, water cannot get in through the glass, but it can get in through the sides. And that's what's shown here at this zoom in as well. Of course, you can improve it by using a better quality encapsulant at the front. So they only changed the encapsulant at the front, and then the loss went down from 8% after 3,000 hours down to 3%, which is acceptable. So it clearly indicates that the TOPCon at that time, because there has been a lot of movement, which I will explain later as well, had a sensitivity at the front. So, and that's basically what I will go through in this presentation. So I will explain a number of failure modes, a lot of them damp heat. We'll also show a bit of how the bill of materials can affect the performance, UV-induced degradation. But unfortunately, I'm not only the bearer of bad news, we also have many solutions for these degradation modes, which I will share as well. And many of them are patented by us. And then I'll present some initial work, how we will bring these lab results to the field, because often companies, they get worried by our publication. They say, like, how is this going to affect my 0.5 gigawatt solar farm? And that's something that requires a bit more work, because you want to predict 25 years of performance with sometimes 1 day of testing. So there's a bit of work needed. But let's first look at damp heat failures in heterojunction at TOPCon solar cells. And this is a paper we published again, I think in 2023, about 4 failure modes in heterojunction solar cells. So that's basically taken from that the second slide I showed. So these new failure modes that we had in heterojunction, and this was work led by Danny, who's also in the audience. She qualified it in basically 3 of 4 different failure modes, basically how they look in EL. So EL and PL. So the first one is really localized failures that seem to be a bit random. I'll show you that they're not really random, but they're more random than the other ones. So the second failure mode is a failure mode that starts at the bus bars and doesn't really progress as much as this failure mode. So actually these two are related. The failure mode 3, which is the most severe one, basically takes out the whole cell basically. So in PL, this one still looks very happy, not so much in EL. So that means serious resistance issue, as I will show you later. And then type 4 is really limited to the bus bars. So it's a combination of something that you only do at the bus bar with the back sheet, of in this case the front or back sheet. So we'll explain those in a bit more detail. Then, of course, module level testing takes long. So this was 1,000 hours. And also, it's a bit hard to get the samples out. So you have to do core drilling, and there's often that can pick up contamination. And it's a lot easier if you can do stuff at the cell level. And that's where we spend a lot of time in my group, developing rapid tests at the cell level that replicate failures we see at the module level. And that's basically what I show in this slide. So these are results at the cell level, where we've been able to reproduce the same signatures at the cell level as we saw in the module level. So that's great. So it means we can easily analyze them. So we also had to do a lot of effort basically to reproduce these failures. So we tried a whole range of different contaminants. So that's something you'll see in more of my slides. So we like to put contaminants on the solar cell, see how they react. So we saw that type 1 is basically contamination. And if you're a vertically integrated solar cell manufacturer in China, then your production line is quite clean, of actually almost clean room type production for your cell and modules. So you will not pick up that many contaminants. But if you're a solar module manufacturer in the United States and buying cells from China, not very likely, but you get them from somewhere else, they might have contamination. And that's actually what we saw as well. So we get cells and then they're contaminated. If we don't do any cleaning, we see these localized failures coming up. So that's really contamination. And I'll show you fingerprints could be one of them. The second and third one are related to soldering flux. So soldering flux is, of course, by design aimed at reducing metals. So it's quite aggressive, but we show that it actually attacks certain components of your paste as well, and that results in failures. And then type 4, we typically only see when we have EVA. So EVA, if it degrades, forms acetic acid, and that can result in this degradation. The cell level testing was also 2 orders of magnitude quicker. So you can start a test on Monday, and on Tuesday you have the result. That's quite nice. So industry really loves this, and we're currently working on making this a standard testing method. But it means we can very quickly test contaminants and changes in the solar cell design. So the first contaminant we look at is sodium. So why do we think sodium is a problem? So this is work published by EPFL at the World Conference in 2022, where they showed also heterojunction glass, where they attributed a significant decrease in performance to sodium getting into the cell, and we'll show the mechanism shortly. And then this was a result from TNO from my home country, the Netherlands, where they showed for TOPCon that the TOPCon module was more stable if you did not add the glass on the front. So they did damp heat testing without the glass on the front, just the EVA. Module was happy. Once they put the glass there, it degraded very quickly. So they reckon it was due to acetic acid that can evaporate if you don't have the glass, but also glass is a sodium source. So we suspect that sodium plays a role. So we see both for heterojunction and TOPCon, we have an indication that sodium may be an issue. So where do we get the sodium from in a solar module? Actually, the answer is what doesn't contain sodium. So the glass contains a lot of sodium. We haven't tested a single encapsulant that doesn't contain sodium. So we've tried quite a few. There might be some, but all of them contain some sodium. And of course, all of us are familiar with PID, so potential induced degradation, where under operating conditions, you actually have a high potential difference between the solar cell and the module. So the module is grounded. Typically, the solar cell is negatively charged. So then you basically attract positively charged sodium atoms. So they get to your module, and they get to your cell, and they can cause corrosion, shunting, and polarization. So not a lot of fun. And what we're looking at here is corrosion. And this was the model proposed by EPFL. It's a bit more complicated, but they say that if you have a glass module, then the water only gets in from the edges. But actually, the water transport through the module actually takes sodium from your glass, and in that way, the encapsulant fills up with sodium, and you still have sodium in your encapsulant. So sodium is just, it will typically get in there. So it's good to test how stable the cells are with sodium. So that's what we did in this experiment. So we exposed solar cells. So we cleaned them first. So we wanted to get rid of type 1 failure and expose them to sodium. And typically we use sodium chloride, which is actually a standardized test for a lot of electrical component testing. So it's quite well accepted in other fields. And then we put it on the front side, rear side, or both sides, and then put the solar cell itself. So this is not a module, this is cell. So we put the cell in the damp heat chamber. So that's accelerated testing, typically 20 hours. And we tested a good old PERC and TOPCon and heterojunction and see how they react differently. So if we look at the efficiency results, and that's probably already enough information in that sense, what is good and what is bad. So if you look at TOPCon really doesn't like sodium chloride on the front. So this is basically front and rear. Front and both sides, we see degradations up to 80 or 90% in 20 hours. So you can even start earlier than you put them in last of the day before. Heterojunction, we see sensitive on both the front and the rear. So basically, the rear here is a bit, of the front is a bit more sensitive, but they're basically both sensitive. And then PERC, the scale is quite different. So PERC is a lot less sensitive. So the front is very stable, and the rear has some sensitivity, but nothing close to heterojunction and TOPCon. If we look at where this loss is coming from, it's really an increase in series resistance. So that's why we showed that first. So that really skyrockets for TOPCon. And I will show you some SEM images that make it bluntly clear why. There's a poor contact, heterojunction as well, and for PERC only at the rear. And then the other parameters, actually, there's not really a material impact because the current loss that we see for TOPCon is basically because the metallization is gone, so we cannot pull out the current. So we're just pulling from the bus bars, not so efficient. So if we then look at the distribution of these of the series resistance, here we show series resistance images, and I'm not sure if everybody's familiar with them, but in this case, bright is bad. Bright means high resistance. Dark means low resistance. And we see that for PERC, the only issue is at the rear, and this non-uniformity is basically the non-uniformity of our experimental processing. But it's not something that's localized, for example, just at the bus bars, as we've seen for heterojunction, for example. So for TOPCon, we see that the rear is very stable, but then the front, basically uniform degradation. Again, not localized. And then if we look at heterojunction, we see that both the front and the rear is an issue where we clearly see some signature popping up, so that can give us some information on what's happening. But these measurements basically confirm what we saw in the IV measurements. So it's a uniform degradation, basically mainly in interaction with metallization. So if we then look at the series resistance, of course, it has a few components, and the main one we look at is line resistance and contact resistance. And actually, we only saw a significant difference in contact resistance, which is great because then we know what to focus on. So the contact resistance for heterojunction increased less than, it's an order of magnitude, but for TOPCon, it's like orders of magnitude increase in contact resistance, and that's fully explaining this performance loss. So we know that it's basically the interface between the metal and the silicon. And the PERC cell, we could actually not detect any difference for the contact resistance. If we then look at the cross-sectional SEM images, we see that for PERC, the front, so this is before stress testing, after stress testing, of course, different samples for obvious reasons, but no material difference. So they look quite similar. The rear, and this was the best performing contact that showed degradation. It looks horrible, so aluminium corrodes very heavily, but because of the PERC cell, you have this aluminium goes into the silicon from this eutectic, and that's actually not affected by this by sodium chloride, so that remains quite stable. So you still have a proper contact and also the conductance. You just lose a bit of line resistance here. Then if we look at heterojunction, then we see for both the front and the rear, we see quite a similar behavior. So the contact before looks a lot more dense, smaller particles, and after the stress testing, we see that it looks less dense. The particles have grown, so we see some, we think it's Oswald ripening, so the small silver particles, they actually grow. And we also see, and that's quite consistent, sometimes we see delamination of the contact. And of course, if the contact delaminates, your contact resistance is going to be very high. So we see the rear contact, it's slightly different in terms of how much metal they put down, but you see the same, and here even a stronger delamination. And the delamination could be caused by our sample preparation, but it also indicates that the adhesion strength has significantly been compromised. And that's, of course, an issue if you go for thermal cycling, for example, after that, which a module always does. So it means that you should always look at multiple stress modes for stability testing. And if we look a bit deeper, then we see basically these particles growing. So the silver particles are getting bigger, and basically the filler material seems to be removed, although we're still looking into that. But I think the main reason why the contact is poor, because these small silver particles, they are critical for the contact, they are removed. They basically become a bigger particle, and that results in overall poor contact. Then if we look at TOPCon, so the rear contact is actually quite similar to the front of the PERC. So it's similar paste. So that one is quite stable. But then the front paste, and this was vintage, it's probably 2022, for TOPCon, we see a massive difference. So this contact completely delaminates, so that explains basically the high contact resistance. And clearly, material has been removed from that contact. And if we then zoom in, we again see that the aluminium, because they add aluminium to the TOPCon contact to get a better contact with a boron diffused emitter, because aluminium is a p-type dopant. But these remaining particles, which are quite big, they're heavily corroded away. And our hypothesis basically is that that corrosion ensures that the contaminant can reach the interface and then also attack the other oxides, like we have lead oxide, tellurium oxide. So it's basically a combination of failure modes. So then we look at soldering flux, because that's, if you still remember, in type 2 and type 3 failures, we had those as suspect. So we look at soldering flux. In this case, we look at soldering flux for TOPCon solar cells. And what we did here was, again, exposing the solar cell to soldering flux at the front and rear. But we took 3 different vintages of TOPCon. So in TOPCon, there has been a lot of development, particularly in the front. So the TOPCon rear is actually quite good already. So the front improvements there can really push your efficiency. And that's the main number the industry is pushing. So they go to lighter diffusion, so higher sheet rows, and the paste, they went higher in aluminum content and also narrower lines. So all can have an impact on performance. So we had vintages from 2019, which when TOPCon commercialization started, 2022 when it was picking up, 2023 just before laser-assisted firing or LCOE was introduced. So, and we'll see how the relative sensitivity of these solar cells is to soldering flux. So this is the TOPCon cells from 2019. So we did damp heat testing for, so in this case 122 hours, 100 degrees, 95 so 100 degrees, 95% relative humidity, and we see that the cells are quite stable actually. So the TOPCon cells in 2019 were actually quite robust. If we look at the same testing for the cells made in 2022, we see a significant increase, and again, it's mainly the series resistance. So it's really the metallization that is affected. So that explains almost full loss in performance that we see for the solar cells. Then the cells in 2023, we had to change the testing a bit. So we had to test 10 times shorter and at lower temperature, because these cells were just completely dead after the same testing. So the cells became a lot more sensitive. And that's basically what we've seen anecdotally. We've been working with the industry continuously that every time we got a new batch before laser-assisted firing, these cells became more and more sensitive. Which is, of course, a bit scary, because there's a lot of this product fielded as well. We also saw that there's a bit of difference between the 2 different fluxes we tried, and these are both commercially used fluxes, so nothing special there. So if we then look at the SEM images, in this case cross-sectional and top view, we see that the contacts, they become actually narrower. So, apologies, so the scale is changing. So the contacts are smaller, so increasing the surface to volume ratio, which is not good if you're sensitive to corrosion. But we see that the contacts show this typical pattern that they get less dense. So certain components, so the aluminium and the oxides, so which is predominantly lead oxide, tellurium oxide, they actually get reduced by the soldering flux, resulting in this failure. So yeah, not good news. But then let's see what happens if you change the bill of materials. So that's the main factor we're changing there is basically the encapsulant and the backsheet. We again look at PERC and TOPCon. So PERC, so this was actually a production line that was making PERC modules, very high quality, no quality issues as such. They wanted to go to TOPCon, and they asked us to help with their bill of material selection. So we selected a few types of EVA, of actually their standard EVA, and then PUE, which is a more expensive, low water vapor transmission encapsulant. 3 suppliers, and I'll kind of give you the name of the supplier for, as you will see, obvious reasons. And then we used 3 types of backsheets as well, and we tested, so PERC mini modules and TOPCon mini modules. They were made at a company, so not at UNSW, so not unoptimized academic processing at a production line, so in a very experienced factory. So these were the results with PERC. So after, this was 1,000 hours of testing, no significant reduction for any of the bill of materials that we tried. So EVA was a standard product. With PUE and backsheets, not really an issue. And all the performance loss that we saw was due to series resistance. So again, the metallization. But then, yeah, and if we look at the EL images, yeah, of course, these are mini modules, so that's of course not their standard product, so there was some handling issues. But the good thing was that whatever, little mistakes were made, they did not grow after damp heat testing. So that was actually a good test to do. But then if we look at TOPCon, then we had to change the scale quite a bit. So this is power loss up to 65%. So more than half of the power gone for the modules, mini modules that were using PUE-C. And basically, it's just sold as PUE. So you really have to do a lot of additional testing, which we're currently actually doing, to see what additives are in there that make it so different from the other two we tested. But we saw that actually EVA, which we know is not a very good choice for PUE, for TOPCon, sorry, 10% loss, which is too much, of course, but it's completely dwarfed by what we see in some PUE combinations. So this paper caused a lot of stir. So this was the paper that we called Buyer Aware. Yeah, please check your BOM before making a TOPCon module, for obvious reasons. And then we see also here, it's all about the metallization. So the series resistance goes up for the modules that fail. So it's not, in PL you would not see anything. And then if we look at the images, so EL images, we see actually some familiar failure patterns coming up. And I will directly go to that slide. So this is the paper we published with 3 new failure modes in TOPCon, so the TOPCon modules. And they look quite similar to heterojunction, and that's what I will go into next. So type 1, type 2, and type 3. And if we then look at type 1, so that's basically random distribution of degradation, which you both see in PL and EL. So that's one that actually has recombination losses. It's also interesting to know that both these modules were made at production lines, so not at UNSW, so not like a student doing this. This is really people who know what they're doing. These contaminants, in this case, we blame it on contaminants, ended up in this module and resulted in these failures. And based on what I previously already shown in the presentation, it's not a surprise that sodium is one of them. So handling mistakes, and so we looked at this. I think these were heterojunction solar cells, where we looked at the failed regions compared to the regions that did not fail. We saw a big difference in sodium contamination. And we also, so that's a paper that's currently under review. We call it hidden fingerprints, where we see that sometimes the handlers used for solar cell manufacturing, you can actually see them popping up after a damp heat testing. So if they are a bit contaminated, so for the heterojunction solar cell, you basically bake it in, and the solar cell is ready to fill in the field. So you have to be very careful for that. So if we look at type 2 failure, which is basically the one we called, I think, type 4 for heterojunction, but it's basically busbar darkening. So it only happens when you have acidic acid formation, so if you use EVA. So it's acidic acid in combination with soldering flux, we believe, because soldering flux is there at the busbars. So, and acidic acid is formed throughout the whole encapsulant. So so there's still a push to go to EVA, but we have to be careful because these new solar cells are a lot more sensitive to acidic acid than PERC before. So type 3 failure mode is the most severe one, because basically it's a failure that spreads throughout the whole solar cell. So the whole solar cell is taken out, and we saw this both in heterojunction and TOPCon. And there the failure mechanism is probably a little bit different. So for TOPCon, so we're doing now a lot of work. So it's we related to an additive. So we see that the additives were quite different from the various POEs. And we feel that that additive is basically taking out the whole metallization, so the contact lines as well. And then for heterojunction, we actually saw significant degradation of the TCO as well. And this was ITO, yeah? So indium tin oxide, so which is more stable than zinc oxide, which is now considered as an alternative. So some of these fluxes, so we related it to soldering flux, actually reduced indium oxide as well. But that's still under investigation. So then we move away from damp heat. So of course, every solar cell, every module we put outside, and it will see UV. So is UV an issue for solar cells? Unfortunately, it is. So this is a study that was published also, I think, only a few years ago. So by NREL, where they looked at the sensitivity, and these are module. I think they were module results. Do you know, Umair? Was it module or cell? Cells.
Modules in the title.
Okay. Yeah. Then, so basically, we see that heterojunction is quite sensitive to UV, so that's we understand that. But then also NPERT, which was a technology that it was produced by a few companies, but the interesting part is that it's basically the same front as the TOPCon. So NPERT was sensitive to UV, PERC was stable, and aluminum back surface fields, surprised that it could still find some, but they were also stable. So then, so TOPCon was not on this sheet yet, but then we have results actually from PVEL in the US. So they test a lot of product. So basically almost every big project that is fielded in the US, modules are tested by PVEL in a sampling way, and they found actually that TOPCon was the worst performer in terms of UV ID. So it's a bit small, so heterojunction is red, so the expected sensitivity PERC quite stable, as was shown in the publication as well, but the worst performers were all TOPCon. So UV ID is definitely a concern for TOPCon. So that's what that's why we started focusing on UV ID. So we built our own system at SURF, and the main innovation we did there was basically to have two different UV light sources, so UVA and UVB. So you see that UVB is pushed more towards the high energy end. So our hypothesis was that if it's related to, and I did not mention that, so this failure mode is mainly related to the breaking of silicon-hydrogen bonds in the dielectric films, the passivation layers. So you need roughly 3 eV to do that. So if you have a high energy photon, you're probably going to break more. So we decided we like rapid testing, so that's why we increased the energy. So we did not increase, like the power is roughly the same, so around 100 watts. And compared to the AM 1.5 spectrum, we went a bit harder, but we want to see rapid testing, of course. And we did test, in this case, on lifetime samples, so just symmetrically passivated TOPCon precursors, so either the front or the rear. And that's results we actually presented last year at the European PVSec conference. We see that with UVA, we see basically that the saturation current density, so like the recombination, is quite constant. But then for UVB, we see a massive uptake in recombination, but only for the front, for the TOPCon front. So the TOPCon rear is actually quite stable, which is easy to understand because you have the polysilicon that just absorbs all the UV before it can reach the silicon oxide. So for the TOPCon, it's definitely the front is the main concern, and that's the focus now of the industry. Some companies claim they have solved it. So we're working on that now as well to fully understand how it has been solved, and we'll publish that in due course. So then we'll get to the point where we actually show you that you can actually mitigate some of these degradation modes. And this is the first experiment that we did. It was basically using a barrier layer. So coming back again, so something you do in your PhD, it's something that stays with you for forever. So I tried ALOX barrier layers here, and it's actually for a good reason, because ALD are the most, so atomic layer deposited layers are the most compact layers you can have, and that's why they're actually used as sodium barrier in certain other applications. So if sodium is a problem, why not use a sodium barrier to protect our heterojunction solar cells? And some of you might not be aware that we are actually well equipped at UNSW with a pilot scale reactor where we can do 200 wafers per hour double side coating with ALD film. So when people say to me that ALD is slow, then I'll show them this reactor, and then typically they change their mind after that. So this is available in our in SURF. So we double side coat, and then we expose sodium chloride to the front and the rear and see if the solar cells are stable. And we see that if the solar cells are protected by this barrier layer, then they still degrade a bit, but significantly less than if the barrier layer is not there. And the barrier layer, we have it down to like 5 nanometers, and we would have to work with manufacturers to see what thickness is really needed for manufacturing. And this is a process we've patented as well. So then we'll of course also try this for TOPCon solar cells, and the interesting part was it didn't work for the metallization. So the metal induced of the corrosion of the metal we could not really protect because these particles are too big. So the aluminium particles, for example, are a few microns. So that did not really work. But there's another failure mode in TOPCon that I did not have time to go into detail, but that's related to the rear, where in certain conditions, so certain contaminants can actually take out the silicon nitride you have at the rear of a TOPCon solar cell and then degrade the polysilicon. So it's work that we published, I think 3 weeks ago. So it's quite bad. So once we fixed the front, this is now a new focus for our group. But the good thing is that we could basically avoid this by protecting it with an ALOX barrier layer. Because, and that also explains why the front is not an issue, because the front actually already has this ALOX passivation layer. So you see here that if we don't have the barrier layer, the cell looks quite bad in EL. Of this actually PL, because it's a recombination loss mechanism. But then with the ALOX barrier layer, it works. So that's good. So our patent still works for TOPCon as well. So then another innovation is this laser-assisted firing, or LECO, that probably most of you have heard of. It was introduced to increase efficiency, because you can you separate the standard firing process in 2 steps. So you have the standard firing typically at a slightly lower temperature, and then a laser process where you illuminate the solar cell with laser light very locally under reverse bias. You draw a very high current, and that actually improves the contact locally so much that basically you only need a limited contact fraction under the contacts to get the same contact resistance. So basically you have a partly passivated contact. So it's basically like a PERC equivalent contact, but instead the PERC type contact under the metallization. So that's not actually making it more stable, but the fact that you can use different paste. So the typical LECO paste contains less aluminium or even no aluminium. And that's what we did here. So we tested cells made with LECO paste without aluminium. And basically even our very tough sodium chloride test, the cells were not budging. So they were stable. So that was really a nice result. So that's also confirmed in the series resistance images. And then we see that the LECO paste, it's a bit small, but we see that it's not affected. So before and after, they look quite similar. And then, of course, the proof is in the pudding. We made modules with our industry partner Jollywood with LECO cells and baseline cells, and we showed that the LECO cells, which they call, so they have their own laser-assisted firing process called the Jollywood Special Injection Metallization. We showed that the cells were then of the modules were stable, and also here you can see the real benefit of this enhance firing, that you get a higher voltage, because that's the main driver for laser-assisted firing. Basically, you have locally passivated, like a PERC equivalent metallization on the front. And with the additional benefit that it's more stable against sodium chloride. So then another method we also patented is basically just adding 1 micron of copper. So just do a copper plating on top of the contact. So then you can use any paste, and that actually makes the cell stable against. So again here, the sodium chloride test, we see that the cell is very stable because plated copper is quite compact, and again there's no pathway to get to the interface. And then so the cross-sectional SEM images show that we have this. It's like an equivalent of this barrier layer. Instead of atomic layer deposition, you use plating, and you can go a bit thicker, because for the TOPCon metallization we had to go to a thicker barrier layer. So then the final part of my presentation is basically trying to predict how this will translate into the field. And it's something we're still working on, so it's not a completed story. But being a solar cell or a module is very tough outside, because you have all these stress factors coming at you and can lead to a whole range of degradation modes. So that's hard. And typically in the lab, what we do, we have one stressor and then look at one failure mode. And in the field, you're exposed to all these stresses at the same time. So and that's a big part of our testing as well. We look at this combined testing of combined stress and how that affects the module performance. So we do that by modeling, which is not a surprise, and we then try to design the best lab-based experiments, but then also interpretation of global data, because these stress factors are, of course, not equally distributed over the world. So we know that Australia is a lot warmer than the Netherlands, one of the main reasons why I'm here. Singapore was too humid, so one of the main reasons why I'm here. And then UV, that's it's also tough to be in Australia, because UV is quite high here. And then there's actually very recent work from Shukla in my group, who has worked on so what is the UV degradation over, if you look at globally, with a new decomposition of satellite data, because we wanted to look at how is it different for a tracker system versus, for example, like the 5B approach. So 5B, of course, because it's fixed tilt, east-west, it will see less UV, so which is good for degradation, and we wanted to quantify that. But you also see that being a tracker in Australia is a lot harder than being a tracker in Europe. But the most shocking thing for me was that the IEC test, so everybody says my module is certified, so then you basically guarantee that it can survive 15 kilowatt hour, which is less than 50 days in Arizona. For how can you predict 25 years of performance with saying like, I tested for 50 days, so I'm going to be all right. So that's a strong focus of our work as well. Then if you look at photo degradation, so that's a combination of UV and temperature, you see again that the tropics is a tough climate for modules in general. Australia also not too bad, and most of the standards are based on 25 years of prediction in Europe. So that's why, like, most of you know I'm a very strong proponent of increasing the testing standards, and that's basically what's shown here. So everything that has the same color would have an equivalent. So if it's just a thermal degradation mode, so if we test it for Australia, it would not do as well in Africa, for example, but then in Europe, that module would not have an issue. So I really think we need to go to like modules that desert type modules or tropical modules that are where just you make different choices. So more expensive encapsulants for the tropics, and maybe you can go a bit more conservative, often less conservative in Europe, for example. So to conclude, like you see, a big theme of our group is to go for rapid testing. So because we want to get quick results, and also when we do testing at the cell level, we can actually understand the root cause a lot better. we were the first to report 4 new failure modes in heterojunctions, not to the delight of the industry. And then we had 3 new failure modes in TOPCon. That was probably even less popular, but nobody has shown us that it actually was unwarranted. And fortunately, now the industry is working on solving it. Then we've shown that a lot of these failure modes are related to the metallization, and then particularly sodium and soldering flux is a component that you should focus on. This was probably our most famous paper, that the bill of materials can affect reliability, so a significant degradation if you make the wrong choices. But fortunately, we have cell level solutions, and like the laser assisted firing is now used by almost everybody in manufacturing, so that very high sensitivity is out of the product now, but it's not the end of the story, because there are still sensitivities in these solar cells, which I will report on in future papers. And then we're working on bringing these lab results to the field to help basically people understand what the impact is of these sensitivities at the LCOE. So thank you for your attention, and I'm happy to take questions.
Thank you very much, Bram. Very interesting indeed. Questions?
Martin?
I've got 2 actually. You attributed the benefit of copper plating to the density of the copper. Would plating silver have a similar effect, do you think?
I would think so, yeah. Yeah.
The other one is, there's a lot of interest in edge isolation now that the cells have such large lifetimes, and I've seen, aluminium oxide, ALD aluminium oxide mentioned in that context. When you coat your devices with aluminium oxide, could you fix up the edges at the same time?
Yeah, correct. Yeah, so that basically would be 2 for the price of 1. We had a patent on that, but Fraunhofer just beat us by a few months. So
that's fixing up the edge.
Yeah, fixing up the edge. Yeah, but also most like heterojunction solar cells are now being produced after cutting. So basically, they get the edge passivation as part of their standard process, because otherwise your losses are really substantial. Because when your voltage gets higher, and with the TCO, it's a highway for recombination.
Yes, we've banned shading the cells from our efficiency tables now for some of our categories, because it was making quite a difference.
It's really material there. So we did simulations. I think it was 0.3 for a PERC cell. So at that time it was quite a while ago. But even for PERC, for a half cell, you lose like 0.2, 0.3 if you go to 2 cuts.
Yeah, that seems to be the type of difference you're getting for TOPCon and all that.
Even more, because of the TCO, you actually have an additional transport for recommendation.
Oh, thanks for the good talk.
Thank you.
Any more questions? I have one actually.
Okay.
The allox layers and the laser firing seem excellent ways to deal with the increased sensitivity of cells. But that trend you showed about newer cells having higher sensitivities, is that likely to continue? And will those mechanisms have to be modified in order to improve or reduce the sensitivity?
So in principle, it has been reset now. So basically, this was a trend that we saw with before laser-assisted firing, and now it's reset.
Yes.
Unfortunately, there's other sensitivities that are being introduced, because laser-assisted firing is not fully understood, and some of the failure modes we see are not consistent with the current understanding of the process. So there's still some work to be done. One thing is, of course, you're so close to the fundamental limit that any additional recombination, every additional femtoamp is going to bite. So if you're, for a PERC cell, a femtoamp did not matter that much, but if you're close to the fundamental limit, everything matters. So that's why the recombination at the rear that we just published a few weeks ago, that's quite a minor degradation compared to what we saw previously, but it's because these cells are super sensitive. They have a few femtoamps at the rear, and if you double that, you directly see that.
Yes.
So you go from 4 to 8 femtoamps, but
Okay, yes. Okay, thank you. Mark?
Bram, thanks. Nice talk. Why do you focus on damp heat and not some of the other standard tests like humidity freeze, temperature cycle, or something we used to do at CSG Solar was combined cycle, combine 3 on the same sample. After why humidity freeze? Sorry, why damp heat? Why damp heat?
Yeah, because that's where so we work very closely with the industry, who is of course conducting all these tests, and then we focus on the biggest challenge at that time, because we have limited resources.
Okay, but that's what industry identified.
Yeah, so we have one big climate chamber here, as you know, and we have 4 small ones. So yeah, we have to make choices. So we're informed by our industry partners what's the biggest challenge, and yeah, definitely we work very closely with Canadian Solar, and they're very happy for us to publish most of our results. We're very grateful for. So they help us to identify the biggest problems. And then once we've solved them, then we can publish them. Yeah, but yeah, we're working now on thermal cycling, because that's so I show you this adhesion problem. Of course, with thermal cycling that popped up. Yeah.
And the extra degradation you've identified with some types of more recent modules, how does that affect the business situation of these companies that operate on very small margins anyway, with are there potentially much more warranty claims coming, or consumers wouldn't notice?
Yeah, like the question is, we look at the cell, like the sensitivity of the cell. Of course, you can protect it if you use the right encapsulants. The cell is not going to see those stresses. But unfortunately, people thought that you could treat TOPCon the same as PERC, which we clearly showed that that's not the right strategies. But if you're more careful, so like glass, like good PUEs, then these modules, I would not be too worried. I would still put them on my roof, but if that's probably, yeah.
Yeah, there's solutions. Yeah.
Martin? Yeah.
Your work on the UV testing with different lamps and so on reminded me of a talk I went to once, and I think it was by a Japanese group, looking at heterojunctions, but they actually combined the lamps with narrowband filters, and they sort of quantified the threshold for the damage occurring and then related it back to models of what might be happening. So it's just sort of something that occurred to me when...
Yeah, like I think I've seen, so there have been papers done on the, like looking at the threshold, and it's related to the silicon hydrogen bond. So that's the only one that is, that has a bonding energy around that threshold that they identified. So it's around 3 eV. And then of course the higher the energy, the more damage you do. And then the question that we're still working on is basically, this bond breaks, but of course it can reform. But in the meantime, that hydrogen can move around. So how bad is that? And how does that correlate to what we see on TOPCon, for example? So that's the directions we're looking at. I think we're quite close to solving that for TOPCon, not for heterojunction. Heterojunction is a bit more complicated. So much hydrogen in there, and you basically have to look at defect formation in the whole stack. Yeah.
Bram, probably one specific question from me. I think for HJT damp heat testing with flux, you mentioning that the silver grains are growing bigger. Is that what you found?
Yeah, that's so not with glass. So basically, with our corrosion test, we saw that results in some Oswald ripening. Basically, so these particles, they grow. So there's actually, so silver is still chemically active, but then we even see sometimes oxide formation. But the main thing we see is that the silver particles grow, so removal of the small particles, which is detrimental for the content.
So that is under 85 degree, or is... Okay.
So 85, but then with a lot of sodium chloride put on the sample. So it's a stress test. Well, we feel, I show you some results as well, so where like our rapid testing clearly correlates to the module testing. Of course, that's what we're constantly working on. But some of our tests might not be, might not happen in the field in 25 years, for example. But But the failure modes that we saw for heterojunction, that's definitely, that also ripening, I would expect that we see that after 1,000 hours of damp heat already. Failure modes that look very similar, yeah.
Yeah, looks like the heterojunction. I think in one of the tables it showed that heterojunction for UV degradation is better than TOPCon. Probably one of.
It depends on the type, of course. So heterojunction, as you know, there has been a lot of innovations as well. So now so nanocrystalline silicon. So we haven't tested that, and for TOPCon as well. So there's some cells that are actually quite stable, and we're making very good progress in terms of understanding where that comes from. So there's a big variation, as you saw from the p-val results as well. So you cannot just take that experiment from NREL as a comparative analysis of the technology. I think the p-val results are probably more representative of that, where you showed that heterojunction has not as much product on the market, but definitely there is a little bit better in the product, because they put in UV blockers in the encapsulant, of course, than some of the TOPCon product that's being sold.
Okay, yeah, by working with industry, I think you have like Canadian Solar and probably other companies as well. So they are using different technologies, or I mean, in terms of processing, they're probably slightly different. So for this, they can targeting different product qualities, right? So
yeah, and of course they all test for UV ID. Like my main argument for UV ID is that the current standard is just not adequate. If the current standard is 50 days in Arizona for a 25-year product warranty, that doesn't seem to be consistent to me. And even so, p-val, I think they go to 60, so that's 200 days, less than a year. And if it's really a problem, and then the question is it reversible? So that's what we're working on as well. And I know you guys are, so Martin's group is working on that as well.
Okay, yeah, great, thank you.
On that last point, actually, does this requirement for a tougher standard and to the different climatic conditions in different parts of the world, does that mean that we should move towards having different ratings for different countries, or should it be an overall standard which is higher and therefore more expensive?
Yeah, different standard for basically tougher standards, which is already happening. So there's like I was on a publication for a new desert testing protocol, which is more stricter. Then there's insurance companies. Actually, that's actually more towards, like I looked into that yesterday for hail. So there's like a big insurance company that basically says, yeah, your current hail testing, that's not good enough for certain areas. So we want you to test with bigger hail balls. So I haven't even touched upon that. So that will definitely happen. We'll have to see at what time, but definitely some companies. So in the US, p-val is, for example, their tests are a lot stricter than IEC, and most big buyers, they say you have to have your module certified tested by p-val, otherwise we will not buy from you. And I think that would be great if we could do that in Australia as well.
Yes.
Yeah.
Yes, very much so. Okay. There are no more questions. I'm sure Bram's happy to carry on discussing afterwards. So let's thank Bram again for that really interesting talk.
Thank you. Yeah.